What's up, everybody? This is Wallace from A3Academy. It's so good to be back in the studio along with my studio audience. No, you can't actually do that while we're recording. Just be quiet. Today's podcast is going to be on electric dipoles, what they are, how they work, what they do. So let's just get started. So first thing you need to know, obviously, is what a dipole is. So suppose we had this blob of stuff. Doesn't matter what the stuff is made of. Just suppose that on one side of this blob we had a positive charge. This is what we call a dipole. Normally a dipole is signified with this arrow looking thing. It starts on the negative side of the dipole and goes to the positive side. So whenever I use this in this presentation or in future podcasts, just know that that's what I mean. So where do you find dipoles? Well, one of the best examples of where you find a dipole is in water, or H2O. It's a great place to start. We know for a fact that oxygen is a lot more electronegative and that hydrogen is a lot less electronegative. And when you have this difference between one side of the molecule and the other, you get something what's called a polar molecule. And in this polar molecule, since the oxygen is getting all of these electrons, which are negatively charged, the oxygen side of the molecule is negatively charged. This is what we call delta minus. On the other side of the molecule, the hydrogens are more positively charged because they have less electrons. This is what we call delta plus. And what do we say happens when we have one side of the molecule is negatively charged and the other side is positively charged? We have a dipole. And since we know that water will always be a dipole no matter what, we can call this a permanent dipole. Now there are lots of molecules out there that act like dipoles, like the ones that I show here. For the purposes of this podcast, I'm going to be using water because it's the universal solvent and we find it everywhere. So back to the water. Let's take a look at what happens when we put two water molecules next to each other. No, they don't just sit around there. One of them actually changes orientation. It turns so that one of the hydrogen atoms, which is positively charged, comes closer to the oxygen atom, which is more negatively charged. This is obviously because opposite charges attract, and if we were to take another water molecule and put that in the mix, the same thing would happen. In this case, the oxygen, which is negatively charged, will bend toward the hydrogen, which is more positively charged. Now, when the negative end of one dipole is attracted to the positive end of another dipole, we call this a dipole-dipole attraction. If we take a look at something like liquid water, and we take a look up close, you can see all of these different water molecules that are experiencing these different attraction forces between their two dipoles. If I wanted to turn this liquid water into a gas, like water vapor, I would have to break up all of these attractions, and that takes up energy, which means, as a general statement, the more polar the molecule, the stronger the dipole attractions will be. And the stronger the dipole attractions are, the more energy it'll take me to break those attractions. Since it takes more energy, it'll be harder for me to turn the liquid into a gas. So the boiling point will actually go higher. So again, as a general rule, the more polar the molecule, the higher the boiling point. Usually. It's not always the case, there are a couple exceptions. But we don't always need two dipoles to attract each other. Anything with a positive or negative charge will attract a dipole. Here we have potassium iodide. It's an ionic compound and it dissolves in water, which means its ions dissociate into a positive potassium ion and a negative iodide ion. As you can see, the negatively charged oxygen atoms are attracted to the positive potassium ion. The positively charged hydrogen atoms are attracted to the negatively charged iodine ions. There are lots of dipole attractions going on here, which means as a general rule, when you dissolve something in water, it's going to have a higher boiling point than it did previously. So aqueous solutions have a higher boiling point than water. Usually. Sometimes there are exceptions. So if we had a positively charged potassium ion, or any ion in general, and we had a dipole, for example, water, there would be an attraction between the ion and one of the ends of the dipole, either positive or negative. And this attraction is called a dipole-ion attraction. And there are three major things that tell you how strong a dipole-ion attraction is going to be. The first one is the distance between the ion and the dipole. If the ion and the dipole are closer together, there's going to be a higher force that brings them together. The second thing is charge. If the ion has a charge of +2 or +3, it's going to be attracted more to the dipole. The third thing is the dipole magnitude. the difference between the charges of the two sides of the dipole. You can relate these three things in an equation called Coulomb's law, but we're probably not going to go over that in this podcast, maybe sometime later. But first let's take a look at another molecule, O2 or oxygen gas. Well, just an oxygen double bonded to itself, and since both atoms have the same electronegativity, the electron cloud is perfectly symmetric, which means that both the oxygens share electrons equally. But what happens when we put another polar molecule there? The first thing that's going to happen is that the negatively charged part of the dipole is going to brush up against the negatively charged electrons in the molecule. The electrons are actually pushed away from the dipole, which means that the electron cloud gets distorted. When this distortion happens, you can see that there are more electrons on one side than there are on the other, meaning that one side is positively charged and the other is negatively charged. And when you have a difference of charges on both sides of a molecule, then you have a dipole. This isn't a permanent dipole. If you take away the water, the electron cloud's going to go back to its normal shape, there won't be any difference in the charges, and it won't be a dipole anymore. So this is a different type, it's called an induced dipole. And we call it induced because if we took the first dipole away, the electron cloud of the molecule would go back to its former shape. Now everything up to this point has involved some sort of polar molecule or some sort of negatively or positively charged ion. What if we had two run-of-the-mill molecules, O2 and N2? Now both these molecules are non-polar, but we know for a fact that the electrons around them are going real fast. And sometimes an electron will go past the electron cloud, bringing a little bit of negative charge with it. When that happens, the electron cloud gets distorted, and we know from before when that happens, we have a dipole. And when we have a dipole in one molecule, it's going to induce a dipole in the other molecule. So we have an attraction between two molecules that used to be nonpolar. This is what's called London dispersion forces. And these forces are really, really weak, and they're gone in an instant. Like almost immediately, both of these molecules have gone back to the way they used to be. So now that you know about these different intermolecular forces, that's it for today. I'm Wallace from A3Academy, and as always, the more you know, the better you are. Hey, I just got a letter from Pete. I'm gonna see what it says. He's still in Venezuela. But in the meantime, if you like what you saw, make sure to subscribe to our channel or follow us on Facebook or Twitter. If you have any questions, type them in the comments below. We'll see if we can get to them. And so, yeah, see ya.